I'm Ryoda from University of Upachal. So today's I'd like to talk about the two-word exchange server using the block-epsilon circulant, which is the same content that parallel approaches in the previous presentations. And also, we'd like to consider the modern integrative and the CPU GPU system. Yes. Yeah, thank you very much. So today's presentations consists of following 5 sections, but first 2 sections are very similar context to the previous presentation. Then I will briefly explain to the difference. Yes. Okay, firstly, which is the very basic background of parent approaches. And of course, so let's consider the solver who have independent PD programs considering the modern computing systems, so which is a cornerstone of computer science for many applications. And so considering the massively parallel environment, it is not enough to extract the spatial parallelisms, of course. Then we would like to consider the other possibilities to parallelize and parallel approaches, and all at once approach is also here. Yes. Yeah. So first of all, we came up with the parallel and M-bridge method as some powerful parallel approaches. Of course, this method already achieve a very good performance for parallel programs. And unfortunately, we have some difficulty in selecting on appropriate cost-weight operator for hyperbolic problems. Then let me consider another method, diagonalization-based parameter method, which is a block circulant and a block-epsilon circulant, and the parallel also same. So this method can achieve independent convergence for spatial mass size and the taper width, introducing a weighting parameter by assuming the same linear time integrator for all time steps. Yes. Then this works focus on the block diagonalization-based parameter solvers. And this slide shows our motivations and aims of these works. So yeah, block epsilon types, block circulant types preconditioners already provide outstanding convergence even for elevation domain problems. And currently, I have a major bottlenecks in terms of runtime solutions. And the VC preconditioning steps is a very great, but runtimes of VC preconditioning steps account for approximately 90% for my programs. Then we have motivations to reduce the time to solutions by accelerating the VC preconditioning steps on considering the heterogeneous CPU systems. Yes, the strategy is also here. In case of VC preconditioning steps, this method have 2 main kernels, which is a one-dimensional FFT and a block diagonal solving patch. And the first ones, we use the cool FFT libraries for FFT patch. And the second one is a Mewell, which is one of Torino's family for block diagonal solvings, because the coefficient matrices of these ones is a complex Barrett systems. Then using these libraries, we can solve it for complex Barrett method. And lastly, we also introduce the mixed pressions arithmetic to accelerating the BDC preconditioning steps. So firstly, we introduce single pressions for only preconditioning steps. The other part, we perform double pressions elsewhere. So which is today's talks. Yeah. Much. So then from this slide, let me explain the detailed part of block epsilon circulant and or the parallel method. But some contents, the many contents are already introduced in, by Josh. Then, yeah, let me start. Let me reintroduce the algorithms of BDC preconditionings. Yes, first of all, we assume some governing equations, and also assume the some special discretizations or the temporal discretization also. Then after discretizations of governing equations, we can get one time steps equations following ones. So, and of course, all-at-once approaches can construct the space-time global systems using the one sequential time stepping method. And so we can see that all-at-once systems have a block temporal structure with the same time integrator. Then if we solve these systems iteratively and the preconditioning method, we would like to consider the good preconditioner for these type of problems. Okay, then focusing on block temporal structures. Firstly, block circulant preconditioners is also considered, which preconditioners PVC, and introducing the left top blocks. Then these matrices have block circulant structures, and these properties leads to a very good convergence analysis because preconditional systems is diagonalizable when original system is not. And so also introducing the weighting parameter for these blocks, block-epsilon circulant preconditioner. So this method can achieve independent convergence for number of time steps and the spatial mass size with sufficiently small epsilons. Yes. So previously we this slide corresponds to the backward order and very simple one-step time discretizations, but considering the p-step time discretizations correspond to RVEC matrices, and also using the block diagonalization property for these matrices, and we can get the three-step procedures of PVC production steps using the Kronecker delta formulations. And the blue colors, first ones and the third ones, the blue color, this part correspond to FFT part, and the orange one is correspond to complex value block diagonal solver part. Because so if the original systems is a real value, but this eigenvalue is complex, then coefficient of matrices is complex value. Okay. Then considering the three-step procedures, we need to perform how to perform FFG efficiently and how to solve the complex value systems efficiently. This is my main problems. Okay. Then from next section, so let me consider how to implement the BC production steps, so the FFT part with the complex solving part on our CPU environment. Yes. Firstly, let me consider the data distributions. So these techniques already introduced Josh talks. So firstly, which is this diagram. This figure is the space-time data distributions. X-axis is space, and y-axis times. So yeah, considering the space-time polarizations, and we can see that these colored block data distributions. Straightforward method to perform FFT part. We performed FFT considering to each spatial frequency. Then straightforward method need to perform the 1D parallel FFTs. Okay. But which is not good considering the highly parallel environment. Then yeah, we apply the data redistributions using the all-to-all functions and changing from the parallel 1D FFT to sequential 1D FFTs. Okay, then after these redistributions, we only perform the sequential 1D FFT. The number of these applications is corresponding to spatial redistribution size. Then next questions, how to perform the 1D sequential FFT for these ones. Okay, this works considers the four possibilities. The first one, the FFTW packages using multiple core 1D FFT means and FFT core, FFT core, and FFT core, FFT core is also. And the second one, the FFTW packages and the single core for many 1D FFT cases. Yeah, I think this is a slightly good compared to many core. And the last two ones, they're using the QFT libraries, and which is also same the multiple core 1D FFT. And last one is a single core for many FFT. Yes, many plants using the QFT libraries. Okay, then in order to select which method is good, yes, the preliminary experiment shows some result on Vetheria BDX01s, which is each node have Intel CPUs and A100 CPUs, and the problem size is the number of spatial size or number of temporal size is here, and so its bars correspond to following for method, and breakdowns correspond to some redistributions, including the all-to-all communications and the sequential FFT patch and the copy to CPU on CPU. Yes. Yes. So I'm sorry. So FFT only on CPUs and the QFT on GPU case. Then based on a previously the runtime solution, some of this runtime solution is here. Yeah, we can see the fastest case is a single core of many 1D FFT with a QFT library. Then, of course, later we will introduce the mixed expressions arithmetic for these programs. Then, using the QFT libraries, we can choose the types of QFT double complex or the QFT complex, which is corresponding to single expressions variables. Then this works. We choose the FFT libraries as a QFFT with many 1D FFT. Yeah. So in case of second steps, so please let me consider to solve spatial size complex systems with coefficient matrices is BK. So I'd like to want to use the scalable matrix solver for pure complex value systems. Pure complex value systems means to, of course, we also we can solve these systems using the 2x2 real value equivalent formulations, but problem size is 2x2. Problem size is also increased. Then, firstly, I'd like to use the matrix solver for pure complex value systems. Then we choose the Torino's packages and based on Cocos, T-Petras, and the Muru for algebraic matrix method. Sorry, missing some mistypos here. So, yes. So, and in case of Muru packages, which is some object, and provides a C++ template for scalar values for the local or global index types of node. Then, in order to apply the libraries to our programs, and we can specify the STD complex W to scalar patch, or in case of a single questions case, STD complex float to the scalar patch, which is already defined. And considering the GPU environment, which is very easy to switch to the serial node to a CUDA node to specify this, then yeah, our implementations is used Mueller packages in Torino's families. Yeah, lastly, we introduced the mixed expressions arithmetic for basic precaution Zemer's method. So, which is algorithms, which is a very tentative and yeah. So right preconditioned GMLS method. So which is a GMLS part, and upper part is a preconditioning part. Of course, so in order to invert the PVC preconditioner, we can perform the preconditioning steps, the following 3-step procedures. Then, in order to apply the mixed expression strategy to this, so we allocate vector or the matrices in a single pressions, and we apply the single pression QFT, and we apply the single pressions Mueller matrix solver, and lastly, we also apply the single pressions QFT, and we convert to the double pressions lastly. So, which is a also versions of mixed pressure approaches for basic production steps. And of course, sometimes the many iterative methods use iterative refinement approaches to recover the convergence properties. But BEC production steps and the BEC productions provide a very good high convergence properties. Then currently we have no, it is not enough to use the iterative refinement approaches for our problem. Let me explain the numerical experiment sections. Thank you very much. I'm sorry. Okay, so in order to evaluate and our implementations, we use the MIABI systems operated by JC HPC in Japan, and these systems have a Grasshopper 200 NVIDIA super chips. And we also use an NV HPC environment. These packages including the C++ compiler and NVCC and the QFT libraries. And OpenAPI, it's polarized, MPI polarized with the OpenAPI packages with these comparison options. And we also use the Torinos and 16 versions, and including the Cocos or the T-Petra or the Mueller packages. And so this is the solver settings, and we compare the 3 methods. And the first one is a sequential time stepping method, which is a CPU accelerated spatial solvers. And the second one is a VC64 GMLS, which means double pressions VC precision steps. Then in case of precision procedures, we perform the QFT for QFT double complex or Mueller libraries for STD double complex doubles. And lastly, and BC32 GMLS method, which is a single pressions precondition solver. In this case, we use the QFT libraries for QFT complex types, or the Mueller libraries for STD complex approach. Yes. Then we will compare these 3 solvers. The method programs is very simple, and referring to the Green's original paper or the EFS packages. And we perform the 2 experiments, the 2-dimensional diffusion programs or the 2-dimensional convection diffusion programs. Then in this works, let me introduce and let me explain the result of a 2D convection diffusion programs. Yes, so this is the first result in terms of convergence. So we impose the convergence tolerance is a relative residual is smaller than the 10 to minus 10, and the epsilon parameter for BEC equal to mean to 0.5 or 0. multiplied by dt. So this table shows this part is corresponding to number of iterations, number of outer iterations of GMLS, and this is a final residual achieving the convergence tolerance. And the preconditioning is double pressions or the single pressions, and by changing the spatial resolutions or the temporal size, which is fixed domains. So firstly, we can we will focus on the number of iterations is here. In all cases, using the FP32 single precision steps provides the same 3 iterations for all cases. Of course, increasing the spatial size or increasing the number of size, we can see some difference between two achieving the final relative residuals here and compared to here and increasing the here. But for our problem settings and the convergence tolerance is a 10 to minus 10 in this case, which is the same number of iterations. Yeah. Then considering the in this case, single preconditioning steps is a safe and prohibitive choice for our problems for this ones. Okay, thank you very much. So lastly, let me introduce the parallel result focusing on most largest result is a 1000 by 1000 is a 1000 time steps is here. Experiment on Miyabi systems and which is the grasshopper and the superchips systems. So we perform the we launch the 1 ampere process on per node. And so this is a strong scale experiment up to 60 nodes. Then 60 nodes means the equivalent to number of GPUs. And this figure starts from the edge node because smaller node, we have memory limitations over this problem size. Then this figure starting from the edge node to 64 node case. Yes, so firstly, the black dot lines correspond to spatial GPU polarized time stepping method. And comparing to these ones, and we can see very great strong scaling performance of single double pressures or the single pressures and VEC generous. And also, comparing to the colored and the orange lines, and if we single preconditioning steps consistently outperform double pressure preconditionings at every power reasons. Yes, lastly, which difference in order to investigate this difference between two single pressure case or double pressure case. This is the last figure in these presentations. And yeah, focusing on most largest power reasons and 64 node case. This figure shows a 5 component of runtime solutions. And the 5 component means the first 3 parts correspond to 3-step preconditioning steps. The other part correspond to outer GMRS part. And firstly, focusing on last 2 colors, last 2 parts, we can see almost no significant difference, which is the same operations and the same precisions in the outer GMRS part. But so focusing on preconditioning steps and these 3 procedure, and using the single precisions QFT libraries and provides a good reductions and the forwarding steps is this ones and the backward steps is also here. And we can see the good runtime reductions using the single precisions. And unfortunately, in case of a second steps, which is a block diagonal solving part, we can see the slightly improvement is a 1.156. But comparing to improvement rate is a effective part, which is quite small. I'm not sure why small improvement using the single precisions merged with libraries for second steps. Yeah, I'm sorry, I'm not sure currently, and which is the future works to investigate in the further investigations for these problems. Yeah, thank you very much. So let me conclude my works. And my motivations of my works and the PEC preconditioning steps dominates runtime solutions and approximately 90% for my problems. Then this works aims to accelerate and the ZPU steps and with modern ZPU environment in mind. And so we also introduced the mixed operations designs and a single operations for preconditioning steps. The other steps is performed in double operations. And numerical experiments shows the same outer iterations with the significant loss and accuracies for assuming the 10 to minus 10. And so in case of a parallel experiment, our code with QFFG or the neural libraries deliver to up to 1.4 times fastest. Okay, and feature box is also here, and I'm not sure why small speed up in block diagonalization and the block diagonal solving part with mirror packages. Yeah, which is also feature works. And so I will explore the BF16 or half precisions using the tensor cores for CUDA environment, and which is also quite interesting point for me. And so last point is here, and this works empirically shows some effectiveness using the same operations, but we have no comprehensive combines analysis, especially for small epsilons, then which is also quite interesting for me. And this is the future works of this one. Thank you very much for it.
In, I think maybe slide 17 or so, we were choosing epsilon 18. Yeah. Is the minimum of 0.5 or
yeah.
Can you say a bit about why what that choice is?
That choice refer to the original wind papers. So yeah, of course. So we have to optimize the epsilon parameters and changing the more small epsilons, but yeah, which is a practice. Yeah. So I refer to the Rin's papers and this paper using these conditions to choose the epsilon parameters. Then yeah, we will pick up this one. But yeah, we need to try to as a small epsilon parameter to evaluating our method. Yes.
I mean, if your block solves still work, then you can put epsilon down to 4, independently of the time step, at least for the ones that we play.
Yeah.
All the questions, or is everyone ready for coffee? You had another one. Go on.
No.
All right then. All right. Let's chat over coffee and thank our speakers one last time. No.
I just outside. No, really, just no, at least my yeah, both really. Yeah. No, it's really, it's really more making more fun.
I know Matthias realized that it's the same work.
Yeah, I didn't know that there's. I didn't think so. I just talk because I. A nightmare, right?
Presentation.
That's why basically. Yeah, right.
Sessions.
Yeah. You know, and I was quick. I was
Your talk. What you guys have up to?
Yeah.
I'm
already talk about attending this workshop.
He looks very.
So you already
Yeah. Are you? I have to ask.
Just check.
Yeah.
Oh, nice.
Oh, yeah. Oh, my office.